Okay, so let's get started because we have a lot of talks today, very interesting talks. So the first talk today is by George Fourtounis and Yannis from the University from Athens about deep static modeling of invokedynamic. Go ahead.
Oh, hello. I'm George Fourtounis, and I'm going to be presenting joint work with Yannis Smaragdakis on how to statically analyze Java code containing invokedynamic. So, what's invokedynamic? It's a framework that does dynamic linking and relinking controlled by the programmer in a way that's friendly to the JVM. It's a very powerful framework, and we want to analyze it. And the basic reason we want to analyze it is that it has a core API that is a bit dangerous. It does things that are not very secure for efficiency reasons. That's a design decision. Unfortunately, it's a bit dynamic of a framework to analyze. And in practice, we see this problem because we see unsoundness in existing analysis. Call graph construction, for example, may fail for sites using invokedynamic. And there has been some work on analyzing patterns of invokedynamic. There are specific ways, ad hoc ways to handle some specific cases, but the general case still eludes us. So, invokedynamic is not going away. Since Java 8, it has been used for Lambdas and method references, and these are a very common feature of Java code. And since Java 9, it's been used for string concatenation. You have libraries using it for many different reasons, and you have language runtimes using it. In fact, the basic motivation for the introduction of invokedynamic was dynamic languages on the JVM, like today Groovy. And things don't stop here, because invokedynamic, there's currently a proposal underway for the functionality to be present at the source code level, so the programmer can really access it. These are the basic ideas of the framework. I'm going to be showing the basic ideas and then a piece of code to understand them better. So the technology is based on one instruction, one bytecode instruction. And that instruction does linking, but it does linking in a way that's accessible by the programmer. The programmer writes special bootstrap code, and it can put pointers called method handles inside the call sites of the program dynamically. That's linking. And these call sites are also accessible as plain Java objects, so the program can do many things with those call sites. Those pointers, they come in two parts. They come in the form of method handles and method types, and these two notions combine together to give us type-safe method pointers. And that API contains a dynamic code generator. It also contains native code. So that's a difficult API to analyze. Let's see an example here. This is the only code example of this presentation. So if you see this, you will understand the basic idea of invokedynamic. I'm going to show in code before using invokedynamic and afterwards. Before, you have this very simple code, and we're going to examine one method invocation. That's a static method invocation. A call graph edge would point to just one method, that print method of A. And we know that the JIT optimizer of the JVM can optimize this method invocation. It has a very standard semantics. There's only one target. You can inline it. You can optimize it. Suppose now we want to give a different lookup semantics, method resolution semantics, that call, but keep the nice behavior. Keep optimization friendliness. That's how we would do it. We would use here, the magic instruction, invokedynamic, and we would tell it to use our code, the bootstrap method here. And that method will do the linking. We'll put a method handle inside the call site. We'll somehow look it up or find it in some other way, and it will put it on the call site. Here you see that this is plain Java code. It returns an object, and that object is a special call site. It's a constant call site. The JVM knows this will never change. It will point to a single method. I can optimize it. So we keep the nice behavior, but we gain dynamic lookup of methods. The basic ideas, the method type and the method handle, are found here, and they combine to do a lookup and give you back a handle in the call site. So that's it. We switch now our focus to see a seemingly unrelated feature, the lambdas and method references of Java 8. Java 8 introduced them for functional programming. It did also a generalization. It considered every type with a single method as a lambda. And under the hood, it implemented all of these types with invokedynamic. This is a design choice. They could do something else, but right now they use invokedynamic for that. And because simple types, types with single methods, go through invokedynamic, this means that unsuspecting code or precompiled old code can receive such types made as lambdas. So this is a general problem. And we propose a solution. Our solution is to model the framework in its depth, its APIs, its basic ideas, and we will do it by reusing a points to analysis, an existing points to analysis, to help us see into these special objects. And when we cannot find something because it's a black box, because it does dynamic code generation or it's a native code, then we will model it. We will model its behavior according to the spec. That's the basic thing, the first bullet. Just for lambdas and method references, we give a fast variant of our model. We give something that needs less support from an analysis because things have a specific shape. How do we do that in practice? We use DOOP, which is an analysis framework where analysis rules are written as data log rules, and all the analyses are mutually recursive. They can consume data from each other in a way that they can also contribute to each other. They run together. So that was a basic idea. If you are going to remember one thing from this presentation is this slide. This is our approach. We used mock objects to model problematic corners of the APIs. Not real objects. You don't see a real abstract object allocation site. You create a mock object for things that you don't know, but you know their shape. And we use them for all the special ideas in the framework. Our analysis is mutually recursive with a points to analysis, an existing points to analysis, and an existing reflection analysis. Both analyses can be found in DOOP. They are mature. They are very nice. And we consume information from them, and we contribute back to them. So we run together. Now, our mock objects carry metadata. So we use the points to analysis to propagate them in the program. And then we can connect metadata across the program. We can create something that has intended properties. And when it's used elsewhere, we can know that that mock object has that behavior. So we can carry behavior across the program through the points to analysis, the underlying points to analysis. The basic idea of the invokedynamic framework is method handles. Method handles, as I said in the introduction, are like method pointers, but they are a bit well-behaved. They are typed. What do you do with a method handle? The obvious thing is to call it, to invoke it, to pass it parameters so that it gives you back a result. We model that, so we have special rules for method handle invocation. We don't go through the standard Java rules. We pair them with method types. We check their type safety. And we also use mock objects for all the things that are difficult to model. For example, when you call a constructor method handle, behind the scenes you must allocate something, because a constructor constructs a new object. So there we allocate a mock object and we instantiate this. I'm not going to go into the detail of the rule, just look at it from a distance. So, okay, that's the core. You have invocation of method handles, but you must have a method handle. How do you find that? Usually you look it up. So there is a lookup API, which is kind of special because it has two ideas. One is caller sensitivity. To look up something, you must have a write. So lookup objects are tagged by the type that looks them up. And it also works together with classic reflection. It consumes class objects from the reflection world, and it can translate reflective values into method handles. So this API needs special modeling to work correctly. Okay, now you have method handles up to this point. And we proceed to do the actual modeling of the invokedynamic instruction. Invokedynamic calls a bootstrap code. So that's another thing that gets called. So this gives rise to another call graph, the boot call graph of the program. All the invokedynamic locations call boot methods. So we have boot call graph edges. We need to do some special handling of the arguments because there's some shifting happening. And we have to support the full spec, like var args. You call the boot method that the programmer wrote. The boot method gives you back a call site. The call site is like a box for a method handle. So inside there's a method handle. At that point, invokedynamic has been resolved, or it has been linked. That's where the linking comes into place. The invokedynamic call site has been linked. It points to a method through a method handle. What do you do now? You can invoke the method handle. At that point, we reuse previous functionality. We can reuse all the rules that we saw before, method handle invocation rules. So there's a subtle point here that I said that we reuse the points to analysis to look into the call site objects. So we ask the points to analysis to give us back the method handle field inside the call site object. But imprecision there can mean that if you use the same bootstrap code everywhere, its results will contaminate all call sites at the same time. A bootstrap method may be used in many call sites, but you want to be call site specific as much as you can. And here we do filtering. We say yes, of course, at this point many things can come, but the intended type is this. So I can throw everything else away. I can improve precision by that. Now, the general model is that, but for lambdas and method references, we need something without reflection, because reflection analysis, the analysis that we reuse, may be slow for big programs. So here, we built a variant that reuses part of our rules, but tries to stay out of reflection. And that's easy because the invokedynamic layer used for Lambdas doesn't use heavy reflection facilities. So what we do is that we just depend on the points to analysis, and we reuse the non-reflective part of the previous rules. We model the three phases of Lambda creation, as described in the spec, those linkage, capture, and invocation phases. And again, how do we do that? We create mock objects, mock Lambdas, and we propagate them in the program, and then we resolve them at when they are really invoked, at the point of their invocation, of their application. Evaluation. So there are two parts in the evaluation. First, we made a test suite of our own with three programs testing all features of method references, Lambdas, and method handles invokedynamic. The first two are the method references and Lambdas that I said can go through the fast path. The last one is the generic invokedynamic. And here you can see that there is an efficiency to be gained in the fast path case. For the full case, for reflection, you need the reflection analysis, and that's expensive. But you must pay reflection to give you back the big result. For the second part of the evaluation, we used the ready-made dynamic benchmark test suite that also tests dynamic language features for Java, and there are these four benchmarks. The first three are about Lambdas. And the last one is the generic invokedynamic benchmark. Again, you see in the times that the last one is more tough to analyze. That test suite gives us ground truth. So the ticks show that we succeed in capturing the ground truth, except for one dash here, where we fail, but not because of our technique, because of dupe's lack of flow sensitivity. That makes it imprecise at that point, so something that should be reachable, should be unreachable, erroneously appears reachable. So that's it. We can analyze code with invokedynamic. And how do we do that? We model bad APIs. We model bad behavior, black boxes. We use mock objects to connect metadata across the program. For the full case, we need reflection, but we have a fast path variant for Lambdas and method references. That was it. Thank you for your attention.
Okay, thank you. So do we have questions? Let me start with one. I was thinking that you said you do some filtering when you look up these handles in different iterations or different dynamics. Is that something that I can imagine to be similar to like a context sensitivity, or is that something different?
Well, kind of. If you filter per site, then it's like being site sensitive in a way. It's a form of sensitivity, but I don't think it's one of the standard ones, like, I don't know, object sensitivity. Or, yeah.
Okay. So it's a new form of sensitivity.
Yes. You could formulate it as some kind of standard sensitivity by saying it's a method handle object sensitivity. So you can use object sensitivity for that somehow, but I'm not entirely clear on how the connection can be made there.
All right, thank you. Other questions? All right, then let's thank the speaker again.
Thank you.